Hello and welcome to another episode of the Aleph Zero Podcast. We'll be meeting today with Damian Straszak, the senior blockchain developer from our core team, who will guide us through secure multi-party computation, or sMPC in short. sMPC is one of the two cryptographic methods ensuring user safety and privacy on Aleph Zero blockchain, the other one being zero-knowledge proofs, a technique we discussed in a previous podcast episode with Damian. While discussing sMPC today, we will also focus on its influence on the DeFi space. So let's jump into the conversation. Last time we talked about ZKPs. It's one of the core features of Liminal, but not the only one, as there's also MPC or sMPC. But before we dive into that, could you give us a quick recap of what are the zero-knowledge proofs and what do they bring to Liminal?
Sure. So as we discussed last time, in zero-knowledge proofs, we have two parties, a prover and a verifier. And what the prover wants to convince the verifier is that some property of its secret data holds. Okay, so it holds particular piece of data which it doesn't want to reveal, but still convince the verifier that the data is there and it has some specific property. The simplest example of zero-knowledge proofs we discussed last time are digital signatures, where the prover holds the private key as the private data, and the zero-knowledge proof is simply digital signature of some kind of a message it wants to send. But there are many more advanced examples, and in particular you could build anonymous payment system like Zcash using zero-knowledge proofs. So that's what we discussed last time.
Yeah, and from what you are saying, I gather that using ZKPs, we can build a system where, each user can keep their account private, but can you build a private DeFi with that tech, or is there anything that you really cannot do using zero-knowledge proofs?
All right, that's a good question. And it's correct to say that zero-knowledge proofs are very general and powerful, but they have some limitations, right? So in order to explain them, we must remember that there are these two roles, the prover and the verifier. So whenever we want to use zero-knowledge proofs, there must be at least one entity, the prover, who knows the data, the secret data that we want to do something with, right? So while in this kind of applications like payment systems, it's obvious that each user can keep its account balance or this kind of account data, and the whole state of the system is split between users. Then there are many applications, especially in DeFi, where this is not the case, and you would like to have something called a global secret state. Okay, let me explain what I mean by that using a simple example. So in DeFi, you would like to build exchanges, DEXs. And one particular way to build the DEX is using an order book. Okay, so an order book is simply a set of orders from users, and there is a matching engine which takes this order book and essentially matches orders together. Right? Whenever one user wants to buy token A and the other one wants to sell it and the prices agree, then we can match these two orders and let the users trade. So that's the idea behind an order book. So now we have order books that are running on blockchains, but they are fully public, right? So all the orders in an order book are on the blockchain, and everything can see what the orders are, who sent them, and so on. A private order book would allow to hide these details, right? It would allow to have an order book where it is not possible to see who sent which order and what are the order details, right? The price and which tokens the order is about, and so on. So how to do that and what's the important property of such a system? You can easily observe that this set of orders is something that is not really owned by one single user. Okay, so we would need to have an entity who knows all the orders, even though all of them are private, and who would be able to do this order matching. without revealing the orders and so on. So this means that this whole set of orders is something that is not known by any single user, and still we would like to have it in the system in order to keep it functioning, right? So this is what I refer to as the global secret state. And using ZKPs, it's not really possible to achieve that because there is no single prover who knows this data and who can make state transitions. So that's why we need something else.
Yeah, and when you talk about those global secret states, they sound really like science fiction territory. So I bet you know the answer, but is it even possible to achieve that, or how would you achieve that?
Yeah, when one hears it for the first time, it's really hard to believe that such a thing could be done. I mean, you want some secret that actually nobody knows, but we still can run computations over the secret. So yeah, it sounds mind-blowing actually.
It
Uh,
does.
yeah, and it is, right? So currently there are essentially two categories of solutions to this problem, which people are exploring. And one broad category is using trusted hardware, and the second one is using cryptography. So we here at Aleph Zero are looking at the second category mostly. So these are solutions based on
It's software based, right?
yeah, it's called software based, exactly. So this means that we are not using any specific chips, we are not using a specific hardware. We just run distributed protocols and use cryptography in order to reach this goal.
Does the hardware based privacy require some specific hardware for validators, for example? This is why we are doing it in software based manner.
Yes. So the way that trusted hardware approach works is you need a very specific device, which is called a trusted execution environment. There is a couple of manufacturers that offer that. And essentially this particular device plays a role of a trusted party that keeps the secrets and performs the computation over the secret. So as long as this device is kind of honest and the device is functioning as the manufacturer wanted it to function, then it can essentially achieve this goal of having this global secret state and doing some computation on it.
But you have to trust the manufacturer, right?
Yes.
That he
so
doesn't
you have
do
to
anything
trust the
shady.
manufacturer. You have to trust that the device will not break. You have to trust that no one is able to actually look inside the device. And it's really tricky to kind of prove that it's not possible because it's an engineering problem. And yeah, so I guess there are many interesting directions you could explore using this approach. And definitely there are some projects working on it and making great progress. But of course, there are these concerns that maybe you don't want to trust these devices to a high extent. Maybe some low trust, like we trust them to not leak secrets, but we don't trust them to perform the computation correctly every time. So there is like a big difference between the two, and yeah, there are many trade-offs projects are exploring. It's very interesting area actually.
Yeah, and to those that are maybe new to these types of devices, we are actually using them on a daily basis, right? Those are the enclaves in iPhones, as far as I know, or for example, hardware wallets, right?
Yes, that's correct. So there are many mobile phones that currently have some kind of enclaves that are able to run some kind of specific computation in a trusted way.
All right, so let's go back to the MPC, and could you tell us a bit more on how this software-based approach can be useful for privacy, especially on-chain privacy?
So basically, we have a committee of nodes that is in charge of all the secrets, and they perform the computation over them. And the way it is done is all the secrets are shared using ideas like Shamir secret sharing, and they use some specific multi-party computation protocols to perform computations over these secrets without revealing them. Okay, so the protocols, or at least many of them, are known for a long time. They are basically from the 80s, so it's not something very new. But, well, it takes a lot of time to mature such a technology. So that's why it takes time to bring it to mainstream.
Could you tell us a bit more about how MPC can be useful?
Yes, sure. When it comes to MPC, the possibilities of what you can do with it are pretty much endless. And as we already mentioned, in DeFi, you can bring privacy to many DeFi protocols, DEXs, lending protocols, and so on. You can create private DAOs. You can make a private voting. You can make private decision making in such DAOs. You can do really lots of cool privacy features. And in general, what MPC allows you to do is implement something that you could think of as private smart contracts. So what it really is it's a smart contract whose either whole or part of the state is secret, right? So the committee would keep the state and then we can still do arbitrary computations over this state. So this is really powerful and you can do many things using this idea. So maybe one particular example of what you could do is you could now keep a private key to some account in a smart contract and let the smart contract sign transactions with this private key. So this might not sound very spectacular if you are familiar with smart contracts and how they work, because, well, smart contracts are some kind of agents on chain that have pretty much the same powers as users, right? So they can do things, but in an automated way, which, well, allows us to still think of them as if they were users. But note that they are users only on the same chain as they are deployed. Okay. So with this possibility of keeping a private key in a contract, what you could do is, for instance, hold a private key to a Bitcoin account in an Aleph Zero contract, right? And what it allows you to do is for the contract to essentially act as a Bitcoin user. So this is something that cannot be done using methods we currently know, and it opens really cool ideas. And in particular, it makes bridging very easy. It makes bridging possible between chains where there are no smart contracts, like on Bitcoin. And yeah, this is just the beginning of some cool line of work that would be really nice to look at.
And this is also what we are trying to achieve with Liminal, right? So to offer the MPC keeping the private state of smart contract for other networks, right?
Yeah, definitely the multi-chain aspect is important for us. And yeah, as I mentioned, MPC allows really cool innovations when it comes to bridging. So yeah, definitely this is something that we are excited about.
All right, you mentioned earlier the committee, that this is an entity that is holding the private key in this private smart contract. But like, to what extent can I trust this committee?
Yeah, that's an excellent question. And well, I would say that it's good to compare it with something we already know, which is proof of stake. And we will have essentially the same kind of assumptions as there. So what do we assume about the committee in proof of stake? It really depends on what kind of protocol we use, but typically what we need to assume is that there is at least half of the committee or maybe 2/3 of the committee which is honest. And as long as this is satisfied, nothing wrong will happen to the system. So the consensus will be preserved, the blocks will be coming, the transactions will be executed correctly, and so on and so on. So it's the same thing for MPC. There are many different protocols. All of them have slightly different assumptions. And of course, it's important to pick a protocol which has assumptions that we are okay with. But generally, the assumptions will be that as long as, let's say, half or 2/3 of the committee is honest, no secret will ever leak, and the computation that is being performed by the committee will be correct.
And the computation is made off-chain as far as I know. So how can we be sure that the off-chain aspect is correct, since we don't have the traceability of blockchain there?
Yes, that's also an excellent question.
Thank you.
The answer is also not very straight, I would say, because it depends a lot on what kind of protocol are we really using. So if we use like the most straightforward protocol for MPC, one of the protocols that was discovered in the 80s, then you don't really get a good guarantee on the result. So there is some multi-party computation protocol being run off-chain, and then the parties bring back the result, and they're saying, oh, here is the result, we computed it correctly, and either you trust us or don't. And of course, still, as long as we satisfy the assumptions about the committee, meaning that, let's say, at least half of them is honest, then the answer they provided will be actually correct. So this is still satisfied, but how can we verify it as users? And this is quite tricky. But actually, there are many protocols that came a little bit later, and they're still being developed by many teams and researchers today, that offer something called verifiability. So what it means is that together with the result, the committee also gives us some kind of a proof, a certificate that the result they have computed is correct. So, well, this is really a zero knowledge proof of the correctness of the computation they just performed. So by choosing the right protocol, you can get really high security guarantees here, to the extent of being really sure that the computation was made correctly by verifying this proof that we get from the committee.
Right, and I have this thing on my mind, that what's the worst case scenario? Like, what would need to happen so the private or less secret gets leaked from this committee?
It really depends on what is the way we integrate this multi-party computation protocol in our system. So there are essentially two different ways to integrate. The first way is by saying that we trust the committee to preserve privacy, and only the privacy of the system relies on the honesty of the committee. So essentially what we are saying is the computation, no matter whether the committee is honest or not, the execution of the system will be always correct, because this is guaranteed by some other component. And well, what the committee is trying to give us on top of that is privacy. Okay, so then this is a system which is always computing the correct results. So like, it's not possible to really steal any tokens or do any kind of financial attacks on such a system. And as long as the committee is honest, or let's say half or 2/3 of the committee is honest, then we also gain privacy. So that's the first category of MPC integrations that one can think of. The second category is more powerful but also more risky, and it's also about computation. So we ask the committee to not only be responsible for the privacy, but also for computation. So, well, in that case, they can do pretty nasty things. And in fact, they could steal some keys. They could essentially use these keys to siphon the money from the system. So they could do all the things that normal committee in proof of stake blockchains could do. And well, we believe, and as history shows, this is kind of justified, that they will not.
So they have a stake in that committee, right? Like, what do they have to lose?
Yeah. So that's a great question. It's about staking and whether the committee has to stake some money. And yes, that's of course an important thing to do in case they are responsible for doing computation. So we rely on them with the security of the system, not only the privacy. Then, of course, they need to stake something, and they will lose the stake in case they misbehave. So this is exactly the same kind of mechanism as is used in proof of stake blockchains. This is called slashing, right?
Yeah, and I assume they would have to stake really a significant amount for that purpose, since this is really like a critical feature.
Yeah, that's a big downside, of course, that if we ask them to stake, then the stake will need to be huge in order to secure a huge TVL. And in that case, there is not much incentive for a committee member to really participate, right? Because every member will need to put a lot of stake, but then we need to also allow them to gain something out of it. So it's really tricky to balance the economy, the security, and so on. It's a complex topic. But yeah, I think that, as I'm saying maybe way too often, the proof of stake example and the history of it on many chains shows that we don't have many such attacks in practice. What people attack typically are higher layers like smart contracts and so on. So it's kind of reasonable to believe that this kind of attacks that require collaboration of a large number of parties are kind of unlikely.
Yeah, the risk is just mitigated by that. All right, so from what you just told us, it seems that MPC is really powerful, and I'm now wondering, are they like strictly better than the zero knowledge proofs? Like, do we even need zero knowledge proofs if there's MPC in the privacy framework?
Yes, I would say that in theory, MPC is strictly more powerful than zero knowledge proofs, but in practice, it isn't, at least yet. And the reason is because it's just very fresh. It's not something that people have been working on for a long time, even though and this is a technology from the 80s, really. So, yeah, it requires some time to mature, I would say. And the biggest obstacles to deploying this technology now is essentially that there is either a lot of computational cost to run it, or there is a lot of latency, which comes from the different committee nodes needing to communicate to each other. So the computation is not really quick. And yeah, this is something that many teams are working on and doing lots of progress. So yeah, so the main technical difference here is that while zero knowledge provers are also kind of computationally intensive, they run on a single machine. Okay, so you just need to run a huge computation, but you can use a very powerful machine and then you can make it quicker, right? And yeah, there is also lots of work on making this faster, optimizing the provers, and so on and so on. For MPC, one of the biggest obstacles is that you have many machines, and if you want this to be really decentralized, then you need to keep these machines far away from each other, right? So they should not really sit in one data center, because that would not be really secure. So you want these machines to be geographically separated and so on. And this introduces some latency of communication, right? MPC protocols work by nodes sending messages to each other. And well, depending on how large the computation is, this protocol requires a certain number of rounds. So this means a certain number of messages to be sent between these nodes. And if the protocol requires, let's say, 100 rounds, and the latency is even 100 milliseconds, then well, you can quickly conclude that it will take at least 10 seconds, right? So latency is a big factor. There are many protocols that are optimizing for latency. And yeah, I'm really hopeful we will get some protocols very soon that have low round complexity and thus can really bring the latency to very low numbers.
And in the context of privacy solutions for blockchains, there's also fully homomorphic encryption often mentioned. And what would you say that is this technology like competing with MPC, or what's your take on that?
That's a great question to ask just after I talked about different MPC protocols and latency and so on. It's because fully homomorphic encryption, or actually threshold fully homomorphic encryption, this is what is mostly worked on currently by many teams in this context, is a technology that you can use to actually run MPC. Okay, so this is a cryptographic idea to have an encryption scheme that allows you to apply some computation to the encrypted data. And this is actually very nice, especially if you combine it with a threshold decryption. So very roughly speaking, the way it works is that there are some users, they contribute some data to the system, and all the contributions are encrypted. And then we perform some computation on this encrypted data, and everyone can do that because this is encrypted. And then we get the result. The result is an encrypted result, so we cannot just reveal it. But then we just have this committee, right? This MPC committee who shares a key for decrypting this result. And what they do then is they run a decryption protocol whose result is the decrypted result. So that's really one of the possible ways to run multi-party computation using threshold fully homomorphic encryption. And indeed, this is very promising direction. And it's also one that really has a great latency because you don't really need many rounds of communication here. You just need to execute this computation on encrypted data. This can take some time because this is a very specific encryption algorithm. But after that, the reveal phase is just run in a couple of rounds, which is really great. So I would say fully homomorphic encryption by no means it's a competitor to MPC. It's just one way of realizing MPC. So yeah, it's a very useful technology.
So maybe let's turn to some lighter tones when it comes to all this tech. And you actually mentioned several times that there are many teams exploring these problems that we are also facing regarding the implementation of MPC and privacy. So, giving more context to what we're building as Liminal, how many projects are like aiming to achieve what we're doing with Liminal, like with MPC or combining ZK with MPC?
Right. So yeah, there are countless projects in the KP space, and it's really booming currently, which is a good thing. And yeah, there is lots of open source code being contributed by many of these projects. And yeah, it's a really great community to be in. Some of the projects are also playing with these trusted hardware ideas, with trusted execution environments. So yeah, this is certainly a large group of projects that are doing that, also getting some really nice results. When it comes to projects working on multi-party computation, there are definitely, I would say, 3, 4, 5 of them that are actively working on that. And I guess all of these projects have slightly different ideas. Some of them are working on deployments which are purely MPC. And this is something which might work. But yeah, as I mentioned, MPC is still very young. It's a technology that we believe will shine, but it's kind of early for that. And the approach Aleph Zero is taking with Liminal is some kind of hybrid. So what we are doing is really we bootstrap the system with zero knowledge proofs. So this is our basic solution for anonymity. And then step by step, we would like to include multi-party computation features. So as the technology matures, as it gets faster, as it gets more practical, we will bring more and more multi-party computation into the system. And yeah, we believe that currently this kind of a hybrid system where most of the privacy aspect is dealt with using zero knowledge proofs, and only when it's absolutely necessary we use MPC, seems to be the best approach and the most practical one, at least.
Okay, and what about that MPC use cases that, for example, offer seedless wallets? As we know, this is also like a trend. And I remember that when Ledger announced their recovery feature, like beyond all the noise, it seemed to me that this is also what they're trying to achieve, like split the phrase among few endpoints or devices and try to offer like more convenience for storing your keys while also using this form of MPC for security. Of course, like how secure that was, this is another type of the question. But is this idea of like storing seed phrases as shards, for example, this is also like the MPC?
Yeah, definitely. I would say MPC is a very general term, to the extent that usually in cryptography we like to call it sMPC, where S stands for secure, because MPC is used for so many different things in distributed computing that, well, we really need to have this prefix to make sure we are talking about this MPC where we compute over secrets. And what I talked about today is something that I would refer to as general MPC or universal MPC. So this is really saying that we can perform any kind of computation using MPC. So whatever you would like to compute in a public, let's say, smart contract, you could replace by a computation under MPC. So the committee would do that privately. And well, this is very general, it's very powerful, but of course, in practice, you often want very specific cases of MPC. For instance, computing signatures. Well, this is a concrete computation, and there are protocols called threshold signing protocols that are really MPC protocols that achieve this task. So there are many wallets that offer this possibility of splitting the key into a couple of parts, a couple of shares, keep them on different devices. And this is exactly what we are talking about here. This is using secret sharing to split the data into multiple parts, and then it is using some form of multi-party computation to use these shares to compute the signatures of some messages, right? So this is, I would say, a special case of MPC because it is used for a specific computation. And in many cases, this kind of specific instantiations of MPC are also like very specialized. So they just work for this particular signing scheme or are optimized for this particular signing scheme, whereas they will not work for another one. So let's say it will work for ECDSA, but it will not work for Schnorr and so on. So yeah, this is what you can often encounter under the name of MPC in the context of wallets.
All right, and I have two more questions to go. And the first one, maybe it's a quick one, maybe it's not. Like from your perspective, what Liminal brings to the table? What do you think it's unique in? What do you think is unique in it, and who will mostly benefit from it, especially from the MPC part?
Right. So I think Aleph Zero are one of the first teams who are playing with MPC, who are trying to bring it to the masses. And well, it's not simple. That's something we need to say because this technology is very new. There are not many implementations. In fact, the implementations that are there are typically coming from theoretical papers that are only proof of concepts for academical work. So to really get decent implementations, one needs to do it by himself, which is fine because that's what our work is about. But of course, this technology requires time to mature, requires time to gain adoption, and of course, what I already mentioned, it requires time to get optimized, to get better running times, and to make it just better for the user. Because as you can imagine, large latency, high computational cost, even if happening off chain, are not so pleasant for a blockchain system. So, well, what we are trying to do is to bring this technology to the users, but bring it slowly, okay? Because, well, we could just say, okay, we deploy an MPC system, and what it would probably do currently would be just like a terrible way to interact with the blockchain for the user, because current MPC protocols, or at least the ones that are there implemented, are not very practical yet. So this is something we need to take into account. This is something that we keep working on, and as I mentioned, we will be trying to bring MPC to the users in phases. So the first phase is where we just have zero knowledge proofs, and this is really the backbone of the system that will always be there, by the way, because they are a great way to keep anonymity in the system. But step by step, we will bring MPC features. Maybe first by doing a really simple computation that can give us additional privacy. But step by step, we would like to make the DeFi on Aleph Zero private, and reach out for all these cool applications that we talked about today, and bring them to reality. That's our goal.
Thanks, Damian, for joining us once again on the Aleph Zero Podcast. I'm sure it was so enlightening to our listeners, like what we are trying to build and why we are using sMPC. And thank you to all our listeners for catching up with the Aleph Zero Podcasts. And I want to encourage both regular listeners and newcomers to subscribe on the platforms you're listening to this and leave reviews, as this helps us to get more reach for our podcast. So there's more Aleph Zero content coming down the pipeline, and see you next time.